Hi there, my name is Ken and I'm a PhD student at the University of Washington. I'm here to present our work, Understanding and Supporting Debugging Workflows in Multiverse Analysis, which is joint work with Eunice Jun and Tim Althoff. Did you know that trained analysts, when given the same analysis task and dataset, often come to different and sometimes conflicting conclusions? This phenomenon has been observed in numerous studies and is a major contributor to the ongoing reproducibility crisis in many scientific fields. Many experts believe it is due to the inherent flexibility in analytical choices, such as data filtering and statistical modeling approaches. In other words, the decisions you make while analyzing data can have a huge impact on the results you get. To address this issue, multiverse analysis has been proposed as a promising solution. Unlike the predominant statistical analysis paradigm, where analysts report only a single set of decision options, multiverse analysis requires analysts to specify a key set of decisions and decision options and consider and report the analyses, which include all reasonable combinations. By doing so, multiverse analysis is designed to improve the transparency and robustness of statistical analyses. However, despite the existence of tools such as the Multiverse R library, RDF Analysis Library, and BOBA that have helped analysts in the authoring process, multiverse authoring is still difficult. What are the authoring challenges that, if addressed, could lower the barriers to authoring multiverse analyses? In this work, we identify multiverse debugging as a central challenge. We will hypothesize an initial debugging workflow and outline the challenges associated with it. Based on these challenges, we formulate design goals and build the initial prototype, Multiverse Debugger. With our prototype, we conduct a qualitative lab study to more deeply probe the challenges of debugging multiverse analyses. We synthesize findings to inform a model of debugging, workflows, and highlight design implications. To understand challenges in multiverse debugging, let's follow the story of Emily, who is authoring Multiverse with BOBA. After writing her decisions in a multiverse specification file, Emily compiles it, resulting in over 1,000 analysis scripts or universe files. However, as in normal programming, Emily may have written a buggy analysis. To catch bugs, she runs all her analysis scripts and observes error messages. But with so many universes, detecting errors is slow, and Emily has no easy way of knowing how many unique errors there are and which universes are affected. She may also want to know what the shared analysis decisions in a unique error are to help isolate what the error might be. Moreover, she needs to remember how her changes in a single analysis affect the multiverse specification. To address these challenges, we implement Multiverse Debugger, a suite of command-line tools. First, we introduce Decision Cover, which runs a small subset of universes such that all the code snippets that correspond to each decision option are executed at least once. With this, we can catch a large class of bugs by only running 11 universes. Decision Cover shows the error information of the 11 runs in the error message aggregate interface. This interface, based on the error messages of universes executed, groups unique error messages and shows what the shared analysis decisions are, making it easier for Emily to identify the cause of the error. Emily can now see that there are 6 unique errors and decides to work with the 4th error. She observes the error message in detail and notices that all errors relate to universes that remove Hurricane Sandy from the data and have one specific model formula. She now has a better idea of the error might be a result of, looks at the sample universes that have this error, and chooses to work on universe 447. If she wants to make changes to the universe, she can use the universe to multiverse specification diff to see how her changes will be propagated to the multiverse specification. These are suggestions in which you can then make the final changes in a separate editor and finally save or save and compile. We used our tool, Multiverse Debugger, in a lab study of 13 analysts to develop a model of debugging workflows in the multiverse paradigm. We asked analysts to debug a buggy multiverse specification, starting without a multiverse debugger, and then with our prototype, before finally conducting a semi-structured interview asking about their experience. Our results center around the challenges analysts face when debugging multiverse analyses. Analysts struggle with maintaining a mental model of the multiverse and found it difficult to detect bugs quickly and identify the root causes of these bugs. Without Multiverse Debugger, analysts had no grasp on what the unique errors were and the number of affected universes, leaving them feeling overwhelmed. We also found new insights about analyst workflows. Analysts often started by fixing the first error message, but desired a more strategic way to prioritize bugs. They expressed interest in grouping errors together and identifying shared decisions in error to better understand the bug's impact on multiple universes. We synthesized our observations to a new model of debugging workflows. Moreover, based on these findings, we highlight 4 main design implications that can enhance the effectiveness of multiverse analysis tools, some of which Multiverse Debugger addresses. First, we found that reducing the latency in encountering multiverse errors is crucial. Our lab study confirmed that a long time to detect error messages poses a significant challenge for analysts. The decision cover feature in our Multiverse Debugger proved useful, enabling faster error detection. Future tools should prioritize features that expedite error detection in multiverse code. Second, we confirmed the importance of summarizing unique errors and highlighting shared decision options. Multiverse Debugger's error message aggregation feature directly addressed these challenges, and analysts found it particularly valuable. Therefore, multiverse debugging tools should incorporate error message aggregation to better support analysts. Third, we observed that analysts need support in finding relevant universes and decision options within the multiverse. Future tools should include effective multiverse selection based on universe or decision option constraints. Lastly, we determined that tools that help analysts understand the composition of the multiverse are important. This understanding is essential for diagnosing error messages and identifying potential causes. Our lab study suggests that connecting the multiverse structure to the multiverse specific code could aid in debugging processes. One opportunity to support understanding is through interactive visualization that connect the visualization of the multiverse structure with a visual representation of the multiverse specification code. Such a visualization could support analysts' iterative authoring process, enabling analysts to understand how the composition of the multiverse changes over time as a result of code changes. To conclude, our work focuses on multiverse debugging as a key barrier to multiverse adoption. This work contributes to the first user study to better understand, model, and support the unique challenges that multiverse analysis poses for debugging. In addition, we provide an open-source tool, Multiverse Debugger, that alleviates some of the challenges. We synthesize findings to develop a model debugging workflows and associated challenges, and highlight design implications for future tools to support multiverse analysis debugging. Please read our paper for more details. Thank you.